Alright, in the previous video I ended here, this section 6.3.4. This is not required on the AP, and it's something that I'm going to introduce when we get to chapter 7. So this is not something that I expect you to know. It's just using the normal distribution instead of the binomial distribution as an estimate. So I'm going to skip over that. That's not something I'm going to address in class either. Okay, so the second part of this video is going to be on geometric random variables. So if we take a look at these three scenarios, roll a pair of dice until you get doubles. Attempt a three-point shot until you make one. Keep placing a $1 bet until you win. So here's the difference. For binomial random variables, we had a fixed number of trials, 5, 10, 20, whatever it was. But now our goal is to keep going until we get a success. So this is called a geometric setting. So the trials is not fixed, but the trials are independent and the probability of success does remain constant. So it's independent trials, and we're trying to record the number of trials it takes to get a success. And that probability of success has to stay constant. All right. So let's skip down. I don't like that one. Okay. So again, we can use our calculator to do these calculations. Let's look at this lucky game, I guess. All right. The student will pick a day of the week, and your teacher will use technology to choose a lucky day. If the student gets it right, the class will have 2 homework questions. So basically, you have a 1 in 7 chance of guessing the correct day. So if we look at this question here, this is a geometric random variable. The probability of success is always 1/7, and the trials are independent. The geometric distribution only has one parameter, p. It can't have the parameter of n like the binomial distribution did because we don't know how many trials it's going to take until we have a success. So here's what we have. We have this geometric probability model, and this is your formula. It's basically saying how long you're going until you have a success. So you're going to have, if this is 5, then the first 4 are not going to be a success, and the 5th one is going to be a success. So let's take a look here. What's the probability that the class receives exactly 10 homework problems as a result of playing the lucky day game? So that means the first 9 times they guess wrong, and then the 10th time they guess correctly. So it's the number of attempts it takes to get a correct pick. So this is the probability of failure. We want 9 failures, and we want that first success on the 10th event. So you're 0.0357. Okay, part B. Find the probability y is less than 10. This means the first success is on the 1st or the 2nd or the 3rd or the 4th or the 5th, all the way up until the 9th day. So there's a lot of calculation that goes into this, and the good news is there is some calculator features we can use. So similar to binomial, we can use geometric, PDF, and CDF. So if I bring those up, let me clear this. Yes, I'm sure. So if we go to second vars, again, up arrow, I'm going to see geometric PDF. And that's just going to ask me for 2 values. What's the probability of success? So 1/7. And we want to know that the first success is on the 10th trial. And that's where that probability comes in. And then if I want to know what the probability is that the first success occurs, I think it was within the first 10 trials. Oops. This would be 1/7. I think this is actually 9. So that's how I can use that. That's going to sum up the probability that the first success was on the first trial plus or the 2nd or the 3rd or the 4th or the 5th all the way up through the 9th. So that's how I'm going to use those calculator features. If you have a TI Nspire, you can find that on YouTube, or in the back of the ebook they have a section that shows you how to use the Nspire to do this. Okay, so here we have a probability distribution. The problem is these are all going to have probabilities. I don't know how long, like I said, we can't show the entire distribution because it could be 10,000. But the probabilities are going to continue to get smaller. So one of the things that they're going to ask you to do is figure out the mean of a geometric random variable. So you can see it listed there. It's just 1 divided by the probability of success. So if we go back to the whole idea of left-handers, 10% of people are left-handed. What's the average number of people we're going to check before we find somebody who is left-handed? We're going to need to check on average 10 people. 1 divided by the 0.1 is 10. So one thing that we have to do, I'm looking through some paperwork right now because there's some things that they added to this. And give me one moment. Okay. I don't see it there. I'll mention it in class, but you also have to figure out the standard deviation of a geometric random variable. I will discuss that in class. Okay. I think that's going to be it, and then we're going to hit a summary here. So in 6.3, have to be able to check if a random variable is binomial or geometric by checking bins. For binomial or geometric is going to be without the n. And then if it is binomial, be able to set up a formula. This will be on your formula sheet. Find the mean and standard deviation if asked. And then calculate probabilities based on that using binomial CDF, binomial PDF. Okay, this normal approximation and this 10%, again, not required to do right now, so ignore all of that. Geometric. The main difference is binomial is a fixed number of trials, and we're counting how many successes. Geometric, we have no idea how many trials it's going to take to get that first success. And then we have the formula for geometric probability for that random variable, and then the mean. And again, like I mentioned, I'll talk about the standard deviation in class. So a couple of resources on how to do things on the calculator. And as I mentioned, the Inspire instructions are here in Appendix B, which you can access on your ebook. So, all right, that's it for section 6.3.